Long before humans walked the earth, nature has engineered solutions to its own problems. Through natural selection, organisms have adapted their bodies and behavior to become the best at what they do. From food gathering to reproducing to home building, species use the smartest and most efficient methods to survive. In the past, our designs have replicated physical adaptations, such as Da Vinci's flying machine or more modern Velcro. However, the advancement of technology has allowed us to look past the outward traits and deeper into the microscopic world. Our contemporary understanding of microbiology and chemistry has revealed fascinating things about the processes at work in nature. But what can these discoveries lend to our everyday problems? Using biologically inspired designs is known as biogeotechnical engineering. More specifically, incorporating the organisms themselves or the processes they undergo is referred to as biomediated techniques. These natural additives improve the characteristics of soil for human use, while also offering a sustainable alternative to current soil stabilization methods. In this video, we'll explore how engineers are researching the use of microbes and naturally derived polymers to improve soil's characteristics. We'll assess the current state of these projects and how they might be implemented in the future. Now, here's Lauren with a look at how bacteria can improve a soil's engineering properties.
Perhaps the most relevant natural phenomenon that has inspired biogeotechnical solutions is biological soil crust, a complex matrix of fungi, bacteria, and other microorganisms that coexist in sands of the southwestern United States. These living organisms cement coarse soil particles together, forming layers of soil with all new properties. The binding of sand grains creates larger and heavier aggregates, which have a higher shear strength and more resistant to wind and water erosion. The aggregation of particles also means more pore space is clogged. Because water is blocked from entering the void spaces, the permeability decreases. These properties are often considered desirable in engineering projects. From designing riverside properties that withstand erosion to building more stable and reliable dams, engineers can benefit from the alterations these microbes make to soil structure. In a 2010 study, bacteria, just one of the living elements of biocrust, were used to alter soil properties in sand with successful results. The bacteria was able to alter soil conditions through their natural processes and create an environment that was favorable for the formation of calcite, one of the compounds responsible for binding soil particles together. Through the consumption of urea, the bacteria produce hydroxyl ions, which raise the pH of the soil. This basic condition allows carbonate to form rapidly and bond with calcium, forming calcite. The newly formed compound coats the outside of the individual soil particles, clogging pores that exist between them. Much like the various aggregates in biological soil crust block pore space, the calcite clogs pores in the soil and reduces the permeability. The addition of solids also causes an increase in the shear strength of the soil. When subjected to a shear wave velocity test to measure its stiffness, calcite-modified soil was shown to have a shear strength equal to that of rock. Besides strengthening the soil, this biomediated technique is a safer alternative to man-made grouts commonly used to siphon soil under houses, bridges, or water management structures. Some common synthetic grouts include polyurethane and melamine-based resin, both of which are irritant at best and toxic at worst to humans. Instructions on both chemicals advise to keep it away from potable water. Furthermore, polyurethane is bioaccumulating, meaning its toxicity increases as it travels up the food chain. Aside from being potentially harmful, grouting is not economical. For large-scale projects, a lot of grout is needed to achieve stabilization. Injected chemical grouts are only effective 1 to 2 meters from the injection point and can be unreliable and inaccurate. Because of this, grouting can be costly and time-consuming. Like other biomediated projects, bacteria-altered soil is a new method of soil conditioning and has unique challenges it must overcome before it can be widely used in the field. Calcium buildup blocks pores, which does produce favorable soil characteristics, but also makes microbe transport difficult and creates non-uniform distribution of calcite. Researchers have found that an effective method to combat this behavior is reverse osmosis and evenly spaced microbe injection. These solutions, however, lead to some of the same drawbacks that chemical grout has. The more application needed, the more costly and time-consuming this method becomes. What sets it apart from man-made methods is its sustainability and harmlessness. Bacteria do not pollute the environment like the production and application of man-made chemicals do. However, because it is a new agent being introduced to the environment, bacteria will have an effect on the biota of the ecosystem. If used in the field, Sites must be carefully studied to ensure the microbes used in stabilization will not be invasive or harmful to the native species in the area. However, most bacteria used in laboratory tests are naturally occurring in soil and may pose little threat to humans and other organisms.
Engineering projects inherently alter their surroundings. Unfortunately, these changes may be negative, like accelerated erosion from disturbance of soil and local flora. Excavation, large construction vehicles, and the installation of infrastructure often destroy plants that naturally stabilize the soil. With no plants to hold it in place, the soil is vulnerable to erosion by water and wind, the latter of which can cause major damage by polluting waterways, covering agricultural fields, or causing human health problems. Airborne soils may contain fine particles, which can be inhaled into bronchial tubes where they contribute to increased severity of asthma attacks and lung damage. This is especially problematic in the arid Southwest. Soil here is generally loose, making it more susceptible to wind erosion. Current methods of soil stabilization include frequent wetting of the soil, covering it with geosynthetic mats, or using chemical stabilizers. Unfortunately, these methods are not sustainable due to their high water and financial demands. With climate change contributing to decreased levels of precipitation in the Southwest, the issue of erosion will only get worse. We can instead look to nature for better alternatives, such as using biopolymers to address these problems. Biopolymers are materials that organisms naturally produce, like chitosan and xanthan gum. Chitosan comes from chitin found in crustacean shells, and it's widely available. A study conducted by researchers at Arizona State University found that the spraying of chitosan on vulnerable soils reduced soil loss by wind by 2 orders of magnitude. Chitosan sprays can be a more sustainable alternative to soil stabilization, as they are natural and come from food waste, likely making it less harmful and expensive than conventional methods. Biopolymer sprays have a lot of potential for soil stabilization. However, more tests are needed to evaluate their true effectiveness. We need to conduct field studies to determine their durability in the face of wetting and drying cycles. Also, we need long-term cost-benefit analyses to determine its actual feasibility.
Like all new biomediated solutions, more research is left to be done. It is conclusive, however, that these ecological methods offer a more sustainable alternative to traditional soil alteration. By incorporating the natural world into our engineering designs, we can do work that is better for us and the world at large. The field of biogeotechnical engineering has made use of new techniques that improve our construction materials.
While it is advantageous for us to use these discoveries in our own work, it is a far nobler goal to use them to create a more sustainable world. So there is still an earth to walk after we're gone.